So HPC job scheduling traditionally solved by heuristic optimization algorithms. Today I'm talking about LLM agent for such type of task and highlights its strengths and weaknesses. So hi everyone, I'm Prachi. I'm a PhD researcher at the University of Tennessee, Knoxville and ORNL. So this is a collaboration work between ORNL, USC and ANL. So here's the broader illustration of HPC resource management. An HPC system is a large-scale collection of high-end compute, memory, and storage, which is used to solve advanced scientific problems. These powerful systems, like the Frontier as shown, is shared among users simultaneously. So each user submits their computation as a job by specifying how many nodes memory along with the expected runtime. Because the system is shared, there is a central entity called batch scheduling, which manages all incoming jobs and allocated these resources effectively to them. So this process, deciding who runs what in which order under shared resources, is what we call job scheduling. So it's a inherently multi-objective optimization problem, balancing both system side as well as user side. Our work focuses on exploring whether reasoning LLMs can make these scheduling decisions on the fly. So traditional scheduling methods are highly efficient, deterministic, but often rigid, and they optimize one or two metrics and lack adaptability to dynamic environment. So AI-driven or meta-heuristic methods as well improve optimization through data-driven search, but they depend on training and domain-specific tuning. So their decision logic is often opaque. LLMs, on the other hand, they bring context understanding, adaptive reasoning. So they can reason through about a problem at hand and explain their decisions in natural language, part of transparency, something conventional methods are limited at. So naturally, this brings us to ask a question: can LLM agent dynamically perform this multi-objective scheduling? So at the intersection, we aim to explore how these reasoning models can make balanced, transparent scheduling decisions on the fly to capture both system and user side metrics. So we consider a batch of n jobs submitted dynamically, and each job has attributes like wall time, nodes, memory, and user data. So the scheduler's task is to decide a start time for these jobs in a way that minimizes the objectives like make span, wait time, and maximize utilization, throughput, etc. That too under strict resource constraints. So formally, this agent has four components. The model itself, we are evaluating Claude and O4, which is sitting in a cloud platform. So the input consists of system state, job queue state, and objectives that it has to optimize for, and a scratchpad. So scratchpad is a part of context, a continued memory of its own previous decisions. So based on these input states, model has to suggest or propose an action based on a thought. And everything is happening within an environment, which is also a constraint validator and feedback provider to the model. So this overall abstraction allowed us to systematically test whether this model can function as a scheduler and not just as a text generation model. Here, this slide shows that how LLM interacts with the environment to make adaptive decisions in real time. This environment models the HPC system by advancing time through key events like job arrival or job start or job completion, etc. So we start with the job logs as input. So these jobs are passed to a prompt constructor. The prompt is then sent to the LLM, which reasons about which job to schedule next or which is the appropriate action at that specific time step. And its response goes through the action parser that converts this natural language reasoning into a structured feasible action. That proposed action is validated by a constraint validation module, which ensures the choice is feasible. If it is valid action, the action gets executed within environment and update its resource accordingly, like a job allocation. Otherwise, it appends with a node that with a feedback to a scratchpad. So. And here is the algorithm that summarizes this entire process. It's a simple adaptive control cycle that runs on a cluster of 256 of nodes and 2 terabyte of memory, essentially wholly forming a closed reasoning action observation loop. So here's a prompt structure that steers the model, a role profiling, which defines the LLM's identity, and this helps model to anchor in the right context to solve a scheduling task at hand. Here it comes the environment status, which consists of system capacity, available resources, and different queue status. The decision history, it provides the model short-term memory of its own past scheduling decisions. The objective section specifies the optimization goals like minimizing make span or maximizing fairness by minimizing variance in user wait times, etc. Constraint trade-offs explicitly remind the model of its own resource limits, fairness bounds, and feasibility rules that it has to follow. Finally, formatting instructions enforce the deterministic structure in LLM's responses. So together, these layers make the prompt act like a policy template. And about experimental evaluation, we generated synthetic jobs by sampling each attribute from standard statistical distributions. So submission times, they are generated by sampling inter-arrival gaps from an exponential distribution. The wall times are drawn from gamma distribution, which allows us to control the job length variability. And the resource requests are sampled as powers of 2. For example, homogeneous sort, so these type of workloads simulate consistent job types where all jobs have similar runtime and resource demands. It more like it resembles testing like environment. Then the heterogeneous mixed workload. So this workload has varying sizes, wall times, and memory footprints. It resembles a typical HPC usage pattern. So with the setup above, the first experimental dimension was to test the scheduler performs under different scenarios, workload scenarios. So I'm highlighting just a couple of them that showcases different strengths. So for heterogeneous scenario, jobs vary in wall time, resource demand, and arrival pattern. So the scheduler must balance these conflicting objectives in real time. Each color is a scheduling method, and all methods generate a full valid schedule. So FCFS is first come, first serve heuristic method. So jobs get scheduled based on submission time. SJF is the shortage of first, which prioritizes the shortest wall time among all jobs. And OR tools, it optimizes the job order using constraint optimization to minimize the make span and maximize the resource packing. So based on it, we compute based on the generated schedule, we computed different performance metrics as shown here. So the arrows indicate whether lower or higher values are desirable for each one. On the y-axis, all values are normalized against FCFS, so which is always gonna be 1. And other methods show relative improvement or degradation. So here we can see Claude and OFO perform best overall on the wait time, turnaround time, utilization, and throughput. OR2 achieves the lowest make span, but it does poorly on wait and turnaround time. So it optimizes the overall completion time, but at the expense of wait time. SJF is clearly not so good on the negative metrics here. For another scenario called long job dominant, the workload contains several extremely long and large jobs mixed with smaller ones, as you can see in this plot. So this structure amplifies the convoy effect, like short jobs get trapped behind long ones, so it's useful to test the stress test. So also here, OR2s are the result for OR2s is missing because it failed to produce a feasible schedule for this type of workload. So only SJF and other LLMs are shown. SJF appears to have strong fairness metrics, but that's actually an artifact of the generated workload. So it doesn't consider user identity. So fairness here is incidental rather than intentional. At the same time, SJF performs poorly on wait time and turnaround time. Supposedly, the very metrics is optimized for short jobs. So both LLM schedulers handle this scenario far better. They substantially reduce wait time and turnaround time compared to the heuristic SJF, and they maintain balanced utilization throughput. So between two LLMs, O4 Mini performs slightly better than the Claude in overall aspect. So here is the scalability study. So we increase the scale slowly from job size from 10 to 100. So I'm highlighting here for job size of 10. So for a very small queue, all methods perform almost identically across nearly every metric. There is simply not enough resource contention for different scheduling policies to diverge and show in the results. So the normalized bars are all aligned at 1, which means SJF, OR2s, and LLM-based models are all produce effectively the same schedule quality. So the wait time has excluded because the FCF value is 0. So the normalized metric here becomes undefined. Also, we check the job order for this scheduling, and it is 0. So one interesting difference is that OR2s show noticeably lower fairness. So even at this small scale, it shows lower fairness, while the other methods remain more or less perfectly fair. For the job queue size of 100, the differences between different schedulers become clearer. So OR2s performs very strongly on utilization and throughput, like on a system side, but it does so at the cost of much higher wait time and turnaround time. And LLMs closely follow OR2's results, so, in the positive metrics on the system side, which shows that they can scale their reasoning to pack jobs efficiently. But unlike OR tools, they reduce wait time and turnaround time, giving a more balanced trade-off. For SJF, that method shows poorer make span, wait time, and turnaround time, so its fairness utilization remain close to the FCFS baseline. Now here we look at per decision LLM latency across different scenarios as part of a computational overhead study. So most workloads show similar latency, but the heterogeneous mix scenario here takes longer because the model has to reason through diverse job sizes, complicated resource demands, and fairness trade-offs. So this increases the reasoning depth and produces a wider latency distribution for O4 at least. If we see at Claude results, so Claude remains consistently faster across all scenarios. So, and on the other side, the scalability experiment, O4 shows a spike at 80 jobs, even higher than at 100, as you see. So this is due to the LLM inference variability, where this 80 job run had a broader spread of per call latency. Now, here are some snippets of what LLM actually thinks before making a scheduling decision or proposing action. So it first summarizes the system state, available nodes, memory, waiting jobs, different queue status, and which job is currently running as an acknowledgement. Then it looks at the waiting jobs and identifies key trade-offs like, okay, shortest wall time, smallest resource footprint, and importantly, user fairness. So for this snippet, it notices that user 4 has no jobs running and selects job 5 because starting it both maintains fairness and improves throughput. So it proposes action to start job 5. This is another trace when LLM attempts to propose action which violates the resource constraints as part of hallucination. So the LLM initially identifies like job 32 as a strong candidate among other jobs, which is waiting in a queue because it requires high resources and would improve fairness for a user with no running job. So the agent attempts to start the job, but the environment rejects that action because the cluster doesn't have enough nodes available. So what's important is that LLM adapts and it updates its reasoning, notes that the no job currently fits, notes it knows that no job currently fits at that specific time because of resource availability, and correctly decides to delay until the next running job completes and more resources get freed. So this shows the feedback loop, like reasoning, action, environment, response. In this experiment, we evaluated the statistical robustness of each scheduling method, and each box represents results across different 5 runs, giving us insight into variance and consistency. So heuristics, being deterministic, show flat distribution but underperform in balancing objectives. What we observe is that both LLMs show tight variance bounds and consistently better performance in wait time and turnaround time compared to other methods. So to conclude, reasoning LLMs enabled balanced scheduling with providing transparent decisions. And what we learn is LLMs are better at qualitative reasoning. They can acknowledge and understand different trade-offs and make nuanced decisions. Second, a reasoning process they provide a reasoning process that we can inspect and improve upon. And finally, we found that overhead and adaptivity reveal new frontiers for hybrid design, like considering the traditional scheduling methods with the adaptive LLM-based methods. So we can start combining LLMs with faster and lightweight heuristics. That's all. Thank you.
Thank you.